25 on page 99 says consider an angle of rotation of 60 degrees. So that gives us position A in a circle of radius 1 unit. So I need to zoom in a little bit, but I've shown that that line there is 1 unit. That's the radius. And it lies on circumference of this circle. And we want to show that the triangle ABC, so this triangle in here, is going to be satisfies the Pythagorean theorem, and if it does, that justifies then that angle A, the angle in the corner here, is 90 degrees. Okay, so we already know that this property is in fact true, but we want to prove this. So I'm going to start by working out the sides A, which is our hypotenuse along the bottom, B and C, and we're going to show that B squared plus C squared is going to give us the hypotenuse A squared along the bottom. So since this is a unit circle, we know that the length along the bottom from C to B is going to be 2. So I've given A a length of 2, and then I'm going to find the length of C. So if this line here is 1, if we know this is an equilateral triangle, then we can show that this is in fact this is a isosceles triangle. We can say that this line C is also going to be 1. So we can work that out that way. However, we can do this another way as well. We can use some trig, which I think is what they are expecting us to do. And if we take a look at this green triangle, I'm just going to highlight that here. This triangle, not the green triangle, but this little triangle in here, that is a special triangle. So if we know our special triangle ratios are going to be 60 degrees, 90 degrees, 30 degrees, and it's going to be in the ratio of 2 to 1 to root 3. Okay, so we can also do this in terms of a unit circle and say that that is 1 root 3 over 2 and 1/2. So working out my lengths in this small diagram here, I can see that that length is going to be 1/2. This vertical length is going to be root 3 over 2. We can subtract from the radius to get another length of 1/2 here, and then the length C we can work out using Pythagoras of 1/2 squared plus root 3 over 2 squared equals C squared, and from here we get 1/4 plus 3/4 equals C squared, which C squared equals 1, so C is equal to 1. So we can justify the length C is equal to 1. So I'm just going to fill that in. There's C is equal to 1. I'm going to do the same thing for B. Now for B, I'm going to use this green triangle. Okay, this green triangle which I kind of highlighted there. And the horizontal length here is going to be 1 from C to the origin, and then 1/2 to the vertical. So that is 3 over 2, and then this length here, the vertical length, is root 3 over 2, which we've already worked out. So I'm going to use Pythagoras on that triangle. So I end up with the horizontal 3 over 2 squared plus the vertical root 3 over 2 squared. Okay, and that's going to equal the hypotenuse, which is that diagonal line from A to C, and that's B squared. So I had 9 over 4 plus 3 over 4 is equal to B squared, and that's going to be, just double checking that I have done this correctly, yep, 3 over 4, and then we end up with 12 over 4 is equal to B squared, so that's equal to 3, so B is equal to square root of 3. So plugging in square root of 3 here, I'm just going to now test. I've got my lengths of the outside of that triangle, and I'm just going to test that in Pythagoras theorem. So 3 squared plus 1 squared must be equal to the hypotenuse, which is along the bottom, of 2 squared. And this is in fact true because I end up with 3 plus 1 is equal to 4. So this satisfies Pythagoras' theorem, which means then not only does it satisfy Pythagoras' theorem, it also proves that the angle in the corner here must be 90 degrees.